Welcome to this video on capacitors in series with one another. And if you haven't watched the introduction of the multiple configurations of capacitors, you want to go back and check that out so that this will make a lot more sense for you. So let's go ahead and connect two capacitors in series with one another, which means don't have a split between them. So here's capacitor 1, and then I'm going to draw a wire to capacitor 2, and then I will also have those two in series with a battery like this. And I'll call the battery B1. Now, let's talk about what should happen. And the same rules will apply no matter what, and so we just have to adapt them to this situation. Remember, the role of the battery is to do work, and the work is going to pull some electrons off of this plate, and it's going to dump them onto this plate, and we've seen that happen before. Now, for sake of simple explanation, I'm going to say this battery is able to pull 4 electrons off of this plate and dump those same 4 electrons onto this plate. I'm going to also label some points in my circuit. I'm going to call this point over here point A, this point B, point C, D, E, and F, just to make things a little easier to describe. What I'm going to say is that the voltage at point A, right, is less than the voltage at point B initially. And so that's why electrons move, right? Because remember, electrons will move from low to high potential, and so there will be a flow of electrons in this direction. That means that C and D also have to have the low potential side or the high potential side, whichever way you look at it, and that's why the electrons dump onto the other plate. Once this has happened, what we're going to say is that plate A over here is going to be left with 4 holes because I removed 4 electrons. And those 4 electrons have been dumped onto plate D, meaning there are 4 excess electrons on plate D. Now, if we think about the plates F and E, they're isolated from the rest of this part of the circuit because there are gaps in between here, and the electrons cannot move through a non-conducting path. And so what's going to happen in between here, this is all metal, that the free electrons are going to be repelled by the electrons on this. So what I'm going to see happen is another 4 electrons, which are not the same as these ones, right? They're going to flow in this direction because they're repelled by the ones that were placed on D. That's going to leave plate E with 4 holes. And plate F is going to have gained the 4 electrons that were lost from plate E. So I see this setup where I have a positive and a negative plate in one capacitor and a positive and a negative in the other. And you can see that it would be impossible to flip the signs on plates D and E if A and F stayed the same, because then you would not have had charge conserve. You would have invented 4 electrons here in the middle that came from somewhere else. Now at this point, what we would say is when VA equals VB, the current I stops. So the current stops and we have a fully charged set of capacitors. Now if you think about it, the charge everywhere in the circuit is exactly the same, right? We have a 4 electron charge here, the same 4 electron charge here, except it's positive, of course, and the same goes for these two. So what we'd say is that Q1, the charge on this plate, is the same as the charge on the other plate over here, right? And that would be the same for the charge everywhere in the circuit. So we could say that the total amount of charge that's moved, right, is just maintained throughout the entire thing. We haven't added any extra charge anywhere, it's just kind of moved around due to conservation of charge. Now, if we look at this idea that VA and VB have the same potential, thus the current stops, point C, the voltage at point C, and the voltage at point D are also going to be the same, and therefore the current in that side of the circuit will stop as well. At that point, we see that the potential across B to C, right? So that's the potential across the battery, would be the same as the potential across both capacitors like this, right? So if you think about it, if we were to connect a voltmeter, so I'm going to symbolize that with a circle with a V in it. Let's say this voltage reads 12 volts. Well, if VA equals VB, VC equals VD, then VA and VD must equal one another because the current has stopped. So if I measure the voltage across both of these together, I will also get 12 volts once it's stopped. Now that means that the total potential difference across the two capacitors is equal to the potential difference across capacitor 1 plus the potential difference across capacitor 2, because they have to add up to the total voltage that we saw. Now I want to introduce the term capacitance into this expression. So what I'm going to do is use my capacitance equation, or my capacitance definition here, and say that delta V is equal to Q over C. So everywhere where I have a delta V, I'm going to substitute in Q over C. So the delta V across A and F, so across capacitor 1, would be Q1 over C1. Across delta 2, or delta V2 over here, would be Q2 over C2, and that's going to show Q total, so the total amount of charge between the two, over C equivalent. Now what we mean by this is that if we were to find one capacitor and replace it for these two, so in place of these two, what would the capacitance have to be of that one capacitor that would make up the same capacitance as these two? That is known as the equivalent capacitance. So the equivalent capacitance you could think of as the total capacitance between these two. Now we've just shown that the charge is the same across both of these, right? We didn't add or subtract any charge. So I'm going to factor out Q here all throughout this, which will just leave 1 in the numerator of each of these equations. So what we'd say is 1 over the equivalent capacitance is equal to 1 over the capacitance of capacitor 1 plus 1 over the capacitance of capacitor 2. Now if I were trying to solve for the equivalent capacitance, CEQ, what I would see is that I would have to do 1 over capacitance 1 plus 1 over capacitance 2 all to the negative first, right? So I would multiply by C sub EQ on both sides and divide by 1 over C1 plus 1 over C2 on both sides to isolate that. So just some algebra. But we see that when we have capacitors connected in series with one another, this is how we would find the equivalent capacitance of those capacitors. And you can add as many of them as you want into the string, and you would just add another 1 over capacitance 3, and so on and so forth. So in series, what we see is true is that because there's only one path, the amount of charge is consistent across all of the capacitors and both together, but the potential has to split between each one in order to have the potential be the same across the edges of the configuration. That leaves us with this expression for finding the equivalent capacitance of the individual capacitors. In the next video, we're going to take a look at the same scenario, but for capacitors connected in parallel with one another.